Now that we've compared and contrasted Java platform threads and Java virtual threads, it's time to walk through the implementation of case study ex15. This case study demonstrates how to create, start, and use virtual and platform thread objects in very modern Java, in other words, Java 19 and beyond. This case study also showcases the difference in performance between Java virtual and platform thread objects. You can find the source code for this example in the ex15 project in the FP folder in my Modern Java GitHub repository. We're now in the ex15 project, where we're going to take a look at the ex15 file. This example demonstrates how to apply Java functional and object-oriented programming features to create, start, and use virtual and platform thread objects in Java 19 and beyond. In order to run this program, you'll need to have Java 19 or beyond installed, together with Gradle 7.6 or beyond configured. We'll start our walkthrough by taking a look at the sPrimality check counter, which is an atomic integer that we use to keep track of the number of primality checks performed thus far, so we know when to print the results to the output. Let's now go take a look at the main entry point into the program. The first thing we do is we parse the command line arguments. These arguments can be set by this configuration script. As you can see here, we enable debugging, so it'll print diagnostics. We're going to create 50,000 threads, either platform threads or virtual threads, and every 5,000 iterations, we're going to go ahead and print out the results so we can see what's going on without flooding the screen with diagnostics. The next thing we're going to do is we're going to create a variable that will keep track of the total number of virtual or platform thread objects to create, which, as we just saw, is going to be 50,000. Next, we go ahead and create random numbers of that magnitude. So we're going to create 50,000 random numbers from some value up to max value of an integer. Here's what this code looks like. We create a random number generator object in Java. We create a list that's going to hold the results. And then we iterate for count times, in this case 50,000. And we're going to go ahead and create ourselves a random number between 0 and count. And then we're going to add to that max value minus count. And that will shift the range of generated numbers from 0 to count to max value minus count to max value. And then finally, we go ahead and add each generated random number to the list. And when we're all done looping, we'll return the list of random integers. So once we've generated those numbers, we're then going to go ahead and run a test program twice. This test program is going to be parameterized with a Boolean that will designate whether to create virtual threads, if the value of the parameter is true, or platform threads, if this value is false. As you can see here, we're going to pass in the thread count, the list of random integers, and then either true or false. We're also going to time this result using the runtimer timeRun method. And we've looked at this method before. This basically is used to start a timer when the computation begins. It runs the test, it stops the timer, and then it stores the results into a hash map that'll be used later to print the results out when we're all done. That will enable us to know what runs faster, virtual threads or platform threads for this test case. When we're all finished, we print the timing results and exit the test. Let's go ahead and take a look at the start threads method. This is what's really kind of driving everything. So start threads again takes the thread count, the list of random integers, and the Boolean designating whether to use virtual or platform threads. We define ourselves a little consumer object here as a local variable that every so often will print out the threads that are being created. So we'll know how we're doing when we run the test. You'll see what that looks like in just a moment when I actually execute everything. The next thing we do is we create a list to hold all the thread objects. And you can see we make this an array list. At this point, we go into a loop that iterates for thread count times, which, as you recall, in our case, is 50,000. Each time through the loop, we're going to check to see if we need to print out the diagnostics. Only every 1,000 or so times will this happen. The next thing we do is we call a factory method that's going to make us a runnable that will contain a large random number to check for primality. And we do that by indexing into the ith location in the random integers list. Here's what the make runnable method does. You can see that make runnable returns a runnable, and it does this by returning a runnable lambda, and the runnable lambda checks to see if the parameter passed in is prime by calling the isPrime method. And this isPrime method just performs a brute force check for primality. Then it gets back a result, and we call the options instance print diagnostic helper method after getting and incrementing the value of the primality check counter. And if it's designated that it's time to print results, we will print out whether the number is prime, which is what occurs if the result is 0, or if the number is not prime, in which case the result indicates the smallest factor. So you can see that we return a runnable. And this runnable that's returned here is then going to be passed into another factor method called makeThread. So makeThread, as you might expect, will either make a virtual thread or a platform thread to run the runnable based on the Boolean parameter that's passed in. So let's take a look at what makeThread does. So makeThread comes here and it checks the value of the Boolean. If the Boolean is true, then we're going to go ahead and make a thread builder that will create a virtual thread. Conversely, if the value of virtual is false, we're going to make ourselves a builder that will make a platform thread. In either case, we now have a builder, and then we take that thread builder and we say, please associate the runnable parameter that's passed in here with that thread builder and make a thread that will begin its life cycle unstarted. So in other words, it won't actually begin until it's explicitly started. So let's go ahead and pop back here and see what we get back. We get back a thread, which is now either a virtual thread or a platform thread, and then we add that thread to the list of threads. When this loop is finished, after 50,000 iterations, we're then going to use the Java for-each method, which is defined on list, which will iterate through every element in that list and call the thread start method on it, because we're passing in thread : start as a method reference to the for-each method. That will then go ahead and start everything. All the computations will begin to run. And then the main thread will once again call the for-each method on the threads list, except this time it's going to go ahead and pass in the thread join method, which acts as a barrier synchronizer. And essentially what's happening here is that this code will not return until all the threads have finished their computations. Notice how we wrap the thread join method reference with the rethrow consumer adapter method. And what this does is it takes something that is going to generate an exception, such as thread join, which can generate the interrupted exception, and it's going to wrap it in a try-catch block so it catches any exceptions that occur and then rethrows them as runtime exceptions. So that's basically the program. Now that you know what the program does, let's go ahead and run the program. So we'll go ahead and run it. You'll see that the virtual threads, which occur first, go whizzing by very, very quickly. I'll come back and take a look at the results in just a moment. But it took almost no time at all to create and start and perform the operations in those 50,000 virtual threads. Conversely, the 50,000 platform threads, as you can see, take a much longer time to run. And in fact, if you look at the timing results that are printed down here at the bottom, you'll see that it was basically 10 times slower to do the computations after starting and running the platform threads than starting and running the virtual threads. Were I to increase the number from 50,000 to 100,000 or a million or 100 million, you would see that the virtual threads take very, very little time to complete, whereas platform threads take an increasingly longer amount of time. They're just chewing up many, many more resources in the platform. If you come up here, you can see what's actually going on. We're creating the virtual threads every 5,000 creations. We print out a diagnostic. You can see this is coming from the main thread. And then once the threads are up and running, then we're seeing the thread IDs being printed off as virtual threads. And you can see here that it's performing computations, checking to see whether these numbers are prime or not, and indicating if they're prime based on the results they get back. That didn't take very long to run at all. In contrast, the platform threads take a much longer time to run. They don't take that long to create. It takes roughly about the same time to create them as it did the virtual threads, but things really start to slow down when the computations run. And that's because the poor operating system on my MacBook Pro, even though it's got a lot of memory and a lot of cores, is straining to keep up with all the memory that was allocated for those platform threads. Once again, we get the correct results back here, but it just takes a lot longer to run. So this is very instructive. Hopefully you found this useful, and it'll also give you a good sense of how to program virtual threads and platform threads, as well as to appreciate the time that they take to create and run. And as you can see, for certain kinds of operations, particularly for CPU-bound operations like checking for primality, virtual threads can be a significant improvement in performance relative to platform threads, especially if you have a very large number of them, as we did here.